Okay, so in this lecture, we're moving from sequences to series, infinite series. And it's a natural extension of sequences, as you'll see from this following definition. So we have the notation I is equal 1 to infinity. Summation of a sub n is equal to a sub 1 plus a sub 2 plus dot 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 plus a sub I. And this just keeps on going forever. Actually, do your textbook prefer I or N? N. Okay, I'll just use it. So this is an infinite series. Okay. And that's all it is. We're adding terms, expressions, infinitely many times. Okay? So with this, we can now introduce what are called partial sums. So the partial sums of this series so S of 1 is just equal to A sub 1. S of 2 is equal to A sub 1 plus A sub 2. S of n is equal to S of n minus 1 plus A sub n. So each of these terms is a partial sum of the full sum. And notice now, for each choice of an index, we have a value. We have a piece of this sum. So we have S1, S2, dot, Sn, partial sums is the sequence of partial sums. Okay? Now, we can talk about convergence. Infinite series converge sometimes. They converge to a number sometimes. Sometimes they diverge. How can we understand the convergence of a series? Well,
Hello.
I said series, not Siri. Okay, so the following is how we define convergence of an infinite series. So, say it's writing I. We say that this series converges whenever the sequence of partial sums converges. And this is defined as normal, like how sequences converge. So if that sequence converges, then the series converges. Right, and this would make sense, right? If we're looking at pieces, ever expanding pieces of this sum, and those values are going towards some number, it would make sense that that's how we should define convergence of a series, infinite series. Otherwise, it diverges. So if the sequence of partial sums diverges or does not converge, then we say that the series diverges. Okay. Okay, so I think it's best to maybe look at an example. 1/2. Okay. So let's look at what happens when we add 1/2 to the power n. So 1/2 plus 1/4 plus 1/8 plus dot 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 all the way off to infinity. We're going to add all of these fractions together. Now, this has an interesting interpretation because of each of these terms, 1 by 1 is less than 1, right? So we can picture this geometrically as like, okay, let's take a 1 by 1 cube. A half would be half the area. So like so S1 is just a half. That's the first partial sum. But then if we add to a half 1/4, so S2 is going to be 1/2 plus 1/4, we can picture that geometrically by adding a fourth. Well, if we cut this cube into fourths, we can just add another fourth. Okay. So now this area would be S2. What about S3? Well, that's a half plus a fourth plus an eighth. Well, an eighth is half of a fourth. So we just cut this fourth in half. And then look at this area. This area shown here would be S3. Now, hopefully you can see that adding infinite things together is going somewhere. Where is this going, right? Like S4 is S3 plus 1/16. S3 was all this business. A 16th is half of an eighth. So that's all that. S5 is S4 plus 1/32. So 1/32 is like here. What do you think this sum is converging to? Where is it going? In particular, where are these values going? What are they getting closer to? Right? So we have a half, we have 3/4, and then, so this is our first term, second, and then we have, so 7/8, and then we have 2 times 7/4, and then we have 15/16. Where is that sequence going? Where the sequence of partial sums we see here, we can interpret geometrically and see obviously where it should be going. It seems like the limit of the partials, it looks like visually it should be 1, right? Because if we keep on having, it looks like it's going to fill the whole area, which has area 1. So how would we show that? Well, we have to show that that sequence does indeed converge. Okay. So how do we do that? Well, we need to know what the nth term looks like. What does the nth partial sum look like? Well, it looks like a half plus a fourth plus an eighth, dot, dot, dot. Let's go ahead and write the eighth. Plus dot, dot, dot. Over 2 to the power n. We need to know what the sequence looks like. This is not the sequence. This thing, this expression, not the sequence. Be very careful with that. I've had a lot of students have problems with that in the past. That's not the sequence. This is the sequence, and we need to find out what that is. And it's actually, you don't even have to work out the algebra to look at it. What's in the denominator? 2 to the power n. What's in the numerator? 1 less than the denominator. You notice the pattern. So this would be 2 to the power n minus 1 over 2 to the power n. So this gives me our sequence. Okay? So then we just need to find out, what does this go to, if anything? Well, this is actually pretty simple. This is the limit of 1 minus 1 over 2 to the power n, right? And we just split that ratio up. And then limits distribute, right? So we have the limit of 1 minus the limit of 1 over 2 to the power n. There's no n here, so the first one is just 1, and then that goes to 0. So yeah, this sum equals 1. We verified it. So if we understand convergence of sequences and limits on sequences, then provided we're able to rewrite the partial sums as a sequence and figure out what its form is, then we can understand the convergence and divergence or divergence of a given series. So, I should probably mention these special series that we might encounter. The first one I want to speak of are telescoping series. So sometimes you will encounter series where you don't need to go through the trouble of figuring out what the sequence is, because the series has a certain form that makes it much easier. And one of my favorites are telescoping series, because I've encountered them in research problems where, like, I'm trying to figure out a pattern and I notice, oh, it's telescoping. What does telescoping mean? Well, it means that the series looks like this. Suppose you have, is it plus or minus should I use? It really doesn't matter. We should use minus first. If you can write your series like this, if you can write it that way, then what should I don't have an example in front of me. Well, I don't know. ready for an example yet. I need to elaborate on this because you probably don't see what I mean. Notice now that this is going to be equal to B1 plus what? Notice this B0, this B2, and that B2, they subtract out, right? But then this B3 and that B3, they subtract out. Then this B4 and that the B4 after will subtract out. So really, what we need to figure out when looking at this is, okay, we have the first term, right? That term is going to be in the series for sure. But what about what's left over? Well, what's left over is, well, let's say maybe, let's look at the partial sums. So S1 is just going to be V1. S2 is going to be V1 plus, how did I write this down here? Hold on. Oh, it's much easier than that. So S1 is for sure V1, but in general, Sn is going to be V1 plus, it's fine, whatever, I'll use their notation, minus Bn plus 1. Their notation is terrible. I'm just noticing it right now. I might want to change it. Yeah, I'm just not a fan of that notation. I'm not a fan of the notation because your book is not specific on how these terms are generated by the series. So I think I do have to introduce an example sooner than I was expecting to really illustrate what's going on. So I think that, yeah, definitely example. 2, 4, and squared one. Okay, so let's look at the sum. N is equal 1 to infinity 2 over 4n squared minus 1. That it? Yeah. Okay. So the a sub n here is just this. This is the expression, right? But notice now that this is a difference of squares in the denominator, which means that we can rewrite this as, so 2n plus 1, 2n minus 1, because it's a difference of squares. Okay, now if we expand this, by the way, do you remember how to expand something like that? Partial fractions. You can use partial fraction decomposition to figure out what this term is, right? So it's like this. If you don't remember partial fractions. So 2n plus 1. These are the linear factors here. There's 1 each. So this is going to be a over the first one. 2n plus 1 plus b over the second, 2n minus 1. Okay? So I guess I'm reviewing partial fractions with us because they will come into play with these theories. So now we just need to figure out what a and b have to be. So I know that 2 is going to be equal to a times 2n minus 1 plus b times 2n plus 1. Now, if n is equal to 1/2, what happens here? So n is equal to 1/2. Then this goes to 0, and then it's going to be 2 times 1/2 is 1. So you'll have 2b is equal to 2, so that means that b must be equal to 1. And then if you now plug in 1 for that, and you make n equal to negative 1/2. So now n is equal to negative 1/2. Then, so what is this going to be? So negative 1/2 of that, so this would be 0, right? And then this would be -1, -2, so that means that a will be negative. So this is really equal to, if I plug in -1 and 1, I can write this as 1 over 2 minus 1 minus 1 over 2n plus 1. This is the key fact right here. Plus, minus, plus, minus, plus, minus, plus, minus. Whenever you see plus minuses anywhere with infinite series, you probably might get lucky, and you might get lucky and be able to write it like this. Right? So how does this help us now? Well, let's just see what happens. So this is going to be, so when n is equal to 1, what do we have? 1 over 2 times 1 minus 1. So 1 minus 1/3. So that's like, this is like A1 right there. Plus A2. So 1 over, so 2 times 2 is 4, minus 1 is 1/3, minus 1/5, plus 1/5 minus 1/7. That is 3, yeah. Do you see it happening now? It's telescoping. So what are we concerned with now? Well, we just need to know where the last terms are going, right? Like, notice that everything is going away except for, in the partial sum case, the very last one. So what is the partial sum? There's for sure going to be a 1 plus what? What's going to be the last thing? So for it might be helpful just to write it out this way, one by one. See that? One more time before I write the general one. Oh. It's just S2 plus, no, all right. Oh, why did I do a plus here? Minus. 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 we see that it has this form, right? As n is increasing. But this is really just 1 minus 1, 7. So what is the general form now? Well, it's just going to be 1 minus 1 over 2 times n plus 1. That very last thing is the piece that's left over in the partial sums. So for telescoping series then, we're only concerned about the limit of this, right? As n gets larger, where does this go? Obviously, it goes to 1 as n gets larger. Right, so the limit of 1 minus 1 over 2n plus 1, it just goes to 1. The idea that the textbook tries to describe is that with telescoping series, it's literally at the nth term, it's your first term and whatever the last term is. That's it. Therefore, for telescoping series, they will converge only when the sequence described by the nth term converges. For example, if that diverges, the whole series would diverge. But because it converges, we're good. And that is equal to 1. Okay? All right, so that's an example of telescoping series. What else do we have? There are geometric series. Okay, so how do they describe it? A non-zero, n equals to 0. Okay. 0, infinity. And a geometric series also refer to finite series. They don't have to be infinite. Okay, where a is non-zero. Okay, so this is a geometric series. The first series that we looked at, the 1 over 2 to the power n, would have been geometric. A would have been 1, R would have been 1 over 2, and n would have been n. Okay? But geometric series are special because there's an actual formula that we can derive for the convergence of geometric series. So we can ask the question, when do geometric series converge? When does that happen? Well, let's figure it out. Okay, so okay. I hate having to explain this one little bit. So this series looks like this. When n is equal to 0, that's just a 1, so it's just a and a r plus a times r squared plus a times r cubed plus dot 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 up to infinity. So in quotes here, it is easy to see that geometric series, or that this sum diverges when R is equal to 1. So according to our definition of partial sums converging, implying the series converges, if that's just a 1, you're just adding A infinitely many times. So it diverges. However, there are branches of mathematics that take exception to adding terms like that infinitely many times. And if you ever see these things, like adding 1 plus 2 plus 3 plus 4 off to infinity, something like that, for example, which wouldn't be geometric, but just when you see that these things converge to numbers, like if you added 1 plus 2 plus 3 plus, you might hear something on the radio, you might come across it online or something. It is true, but it's a different branch of mathematics than what we're doing. So, just had to state that. Okay, but let's just take our definition. So if R is equal to 1, sure, this thing is, we're adding A infinite times, it's not going to converge to anything. So even if it was minus 1, it's easy to see that this will diverge. If you look at the definition that we use of partial sums converging as our definition. So let's just assume that R is not equal to 1 and -1. So R not equal to plus or minus 1. And we're going to say that Sn, the partial sum, we're just going to write it out. A plus AR plus A times R squared plus dot 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 plus A times R to the power N. Okay, so that is the partial sum. And we're trying to figure out a sequence representation of this sum. Okay, well, how can we do this? There's so many different ways to show this. I'm kind of curious to see how they did it. Why do they say this? I am not at all whatever. I don't know what the book is trying to do. I just know that yes, this is the partial sum, right? You have plug in 0, you go to, oh, I see their issue here. Maybe I see it. All right. If you go to the nth term and stop, that's what you get. So I'm going to multiply both sides by R. And you'll see why in a moment. So b squared now plus AR cubed plus dot 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 plus AR n to the power n, R to the power n plus 1. All I did was look at the partial sum and then multiply it by R. And then I noticed that if I add A to both sides, I get A plus AR plus AR squared plus dot dot plus AR n plus 1. Oh, this is the n plus 1 partial sum. So I guess write in plus 1 like that. Wait a minute. So the idea of what I'm trying to get to right now is that I want to write my partial sum in such a manner that it's easy for me to determine if this is going to converge. That's where I'm trying to go with this. And I see that is just, where did I go wrong here? Give me 1 moment. Let me just pause the video. 1 moment. It's gonna take like 2 seconds. I am incorrect about this right here. So we're assuming r is not equal to plus or minus 1. We need an expression for the partial sum. I, for some reason, was not thinking correctly and was writing up the partial sum incorrect, because if you look at S0, it's equal to A, S1, it's equal to A plus A times R. And S2 is equal to A plus A times R plus A times R squared. And the mistake happened is this. N is equal to 0, right? So if I shift my indices, so I can name my sequences should start with index 1. There. That's the mistake I made. Because this series starts at 0 and our sequence is going to start at 1, the index has been changed, right? The last index is this index. The last tower is this index minus 1. So in general, Sn is going to be equal to A plus A times R plus A times R squared plus dot plus A times R to the power n minus 1. Now, if I do my little multiplication trick, it'll work. So multiply both sides by R. So now, this will be A times R plus A times R squared plus A times R cubed, for that one, plus plus A times R to the power of n. Okay. So once we've multiplied both sides by that, what can we do now? If we add A to both sides, one second. So what was I? Something is off, and I don't like it. Oh, no. We're not off. Look at this. We can subtract this equation from that equation. And what do we get? Sn minus R times Sn on the left. And then we have gone. The only thing that's left over is A and AR to the power n. A plus A r to the power n. Now, if we factor out that Sn to the left side, we get that Sn times, what is it, 1 minus r is equal to a plus a times r to the power n. Okay, I'm getting ahead of myself there. Divide by 1 minus r. And that's our term, that's our partial sum. And now it's clear. If r is greater than 1 in absolute value, then this numerator is going to blow up and this is going to diverge. If r in absolute value is between 0 and 1, if it's a ratio like less than 1 in absolute values, then this is going to go to 0 and we're going to be left with what? A over 1 minus r. Let this sink in. If that r is like a -3, then eventually this is going to blow up and the numerator is going to diverge. If that r was a +4, blow up, diverge. If that r, so if the absolute value of r is greater than 1, the partial sums, the limit doesn't exist. Because the numerator blows up. If an absolute value is less than 1, so if that's like a ratio, like think about like a half or something like that, then this is going to go to 0, and you're left with a times 1 over 1 minus r. And there's the formula right there. So if r in absolute value is less than 1, that's our formula. The geometric series is equal to a over 1 minus r. This characterizes when geometric series converge. So, for example, the problem that we did earlier, 1 over 2 to the power n. How is it? So that's a geometric series. Why? Because let's make it better. Let's make it a little bit different. What about like 5 or something? That's geometric. Why? Because this is like 5 times 1/2 to the power n. Now here we go. A is 5, R is 1/2. It converges. What does it converge to? That. 5 over 1 minus 1/2. And 1/2 and the new, yeah, just 10. So geometric series are the easiest. You see a geometric series, that thing is just going to converge, and it's going to converge if the ratio is between the r satisfies this. Otherwise, it diverges. So those are like the best ones to see if you come across geometric series. Okay. Okay, so we have telescoping series, geometric series, but again, everything is dependent on the partial sums in the long run. Like, even if you don't recognize telescoping, if you don't recognize geometric, you should be able to formulate a sequence of partial sums and then use techniques on sequences to determine if the series do converge. Okay. Now also, there are several properties listed in the textbook that you should look at. For example, it should be clear that infinite series with a constant, you can just take that constant out. Right, so this should be straightforward. And it doesn't matter where you start. I also we have two different terms describing. You can rewrite this as like that. Be safe though, provided that like if this converges and that converges, then this converges to the sums on the right. Okay. All right. So one last here. If so if this converges, make sure, yeah. So if this infinite series converges, then the limit of a sub n is equal to 0. Okay. Now a sub n is not the partial sums; it's just the terms of the series, right? So this theorem states that provided the series converges, then you know something about the limit of these terms, which the contrapositive of this statement is that if the limit of these terms does not equal 0, then this series diverges. This is the contrapositive of that statement. Now that is important because we've been asking, like, does the series converge? What does it converge to? The theorem states that if the series converges, then we know something about partial sums. Not partial sums, the terms. But what's more important is the contrapositive of this statement, which says that if the limit of the terms does not go to 0, then the series does not converge. Now that should make sense, right? Like if you have a series and those terms are not getting smaller, right? As n gets bigger, if those terms aren't getting smaller and smaller, then how else would the series ever be going anywhere, right? So, okay. All right. I guess I'll go through the proof of this, and then that'll be it. These are equivalent statements, by the way. This is just the contrapositive of them. All right, so let me prove it. It's supposing that this does converge. So first, suppose converges. So the limit of Sn equals some number L. Okay. Okay. Good. Notice Sn plus 1 is equal to A sub n plus S sub n. Right? The next partial sum, previous plus the new term, which means maybe like thus, A sub n is equal to S sub n plus 1 minus S sub n. Right? I just subtract Sn on both sides. Hence, the limit of A sub n is equal to the limit of S sub n plus 1 minus S sub n. But that is the same sequence as S sub n. These are the same sequences. They both have the same limit. So this would be L minus L, which is equal to 0. So that sequence better converges to 0, which proves this theorem, which gives me this. And I think it's not even a name. Yeah, so this statement right here, this is called the nth term test for divergence. Okay. All right. So from section 9.2, homework suggestions. Yeah, probably just, that's a lot. 11 through 57, just you pick and choose, but do as many as you can. That'll be it for this lecture.